All right, it's 9:30. Let's get started. Thank you everyone for joining. And today we have the honor to present you the Cloud Native Networking Service Mesh, KubeEdge, Istio, Envoy, Cilium workshop. So this workshop will begin right now. So please enable your Linux environment. Ubuntu 18.04 LTS distribution is recommended. Please also install these tools, SSH. The OpenSSH client is installed by default in Ubuntu and Make. If the Make command is not installed by default on the Ubuntu distribution, so do git, golang, docker. We recommended should be higher than 19.03 with the build X, and so you can do the multi-arch. And instructions will be provided during the workshop. So we did. So check internet for your fast reliability and receive the necessary remote VM credentials. I think it's already sent to the email address you used for the DevSummit registration. If you use your personal email or company email, please check it out. All right, this is about the logistics. And if you're experiencing any audio issues with your device, you can use your mobile phone to call in to our workshop. The call-in numbers have been added to the chat. So today we're going to present, which has been is being recorded and will be available within 24 hours on the DevSummit site. You can click the video on demand afterwards. If you have any questions about our code of conduct, please see we have FAQs on the DevSummit site. This is the link. And for any reason the Zoom meeting ends prematurely, please try the link again from the DevSummit site right away. And if that doesn't work, wait for 10 minutes to give us time to add a new link. I assume Zoom is very reliable, but just in case. So we welcome your comments and questions for the speakers. Type any of your questions into the chat box at any point during we have this workshop. Any questions so far? Is it all clear for the logistics for today? Okay. If not, today we'll go through Cilium first, then KubeEdge, Istio, and Envoy. We have the recorded presentation and have the hands-on after each topic. Let me share my Cilium. Can you see it, or shall I? Wait a second. Let me reshare my screen. If you didn't see, let me reshare my screen. Shared my whole screen. Okay.
Hello, my name is André Martins. I'm a software engineer at Isovalent, and in this part of the workshop, I'm going to talk about Cilium and how we can enhance visibility and network security using eBPF on ARM64. This work was mostly done by Ilya Dmitrichenko, which is also a software engineer at Isovalent, as well as Michal Kostecki from OpenSUSE. So let's get started. So what you should expect in this presentation. First of all, I'm going to talk about what is Cilium and what is eBPF, in case you are not familiarized with. And later on, we will build the images, Docker images from Cilium to run these images on your ARM64 environment or ARM64 cluster. We will also deploy this image that we have built in the ARM64 cluster, and finally we will discuss some known limitations and future work that the ARM64 builds currently have. All right, so what is Cilium? Cilium is an open source project that transparently secures your network connectivity and provides visibility for your pods. Cilium runs as a CNI plugin as part of a Kubernetes integration, and as part of the Docker integration is also a libnetwork plugin. With the help of eBPF, Cilium is able to perform network security at layer 3 and layer 4, which means it can perform security to IP and ports. And with the help of Envoy, it can also perform some network security and visibility of higher protocols in the stack, such as HTTP, gRPC, Kafka, Elasticsearch, and many others. Since Cilium controls all this networking of the pods and that goes in and out of the pods, it can also provide visibility with another tool that is available and open source named Hubble. I'm not going to talk about Hubble in this workshop, but just to give you an overview of this tool, it will allow you to visualize all the traffic in your cluster that for the pods that are managed by Cilium. So you have a nice visualization of your cluster, you have a nice network security in your cluster with all of this infrastructure provided by Cilium. All right, so what is eBPF? eBPF is a revolutionary technology that can run sandbox programs in the Linux kernel without changing the kernel source code or loading kernel modules. This is a technology mostly maintained by Isovalent and Facebook, with some collaborations from Google, Red Hat, Netflix, Metronome, and many others. You can find more about this technology in the website eBPF.io, where you can find an extensive documentation as well as some examples and some use cases for eBPF. Cilium itself uses eBPF as part of the networking capabilities that it can provide, but eBPF can be used for many other use cases. In this example on the right side of the screen, this is a small source code of a small eBPF program. What basically does is gets the process name and PID of the process every time it performs a syscall execve, and writes the PID and the process name into a buffering buffer, and that's basically what the program does. And once the program finishes, the request goes to the scheduler from the Linux kernel. As you can see here, the BPF program is running inside the Linux kernel, so it's not running in the user space, it's running in the kernel. Right, so how does Cilium and eBPF work together? So Cilium, as I mentioned before, is a CNI plugin as part of Kubernetes. So every time a pod is scheduled into a node, it sends a CNI event into Cilium. Cilium will then make sure that the pod will receive the right VIF interface and the right IP address for the pod, and it will install the eBPF program on the VIF interface of that particular pod. That small eBPF program will make sure that the traffic goes to the right pod, and also it provides some network policy enforcement, services, and load balancing, so you can perform load balancing as well for each pod. And we can also provide some flows and policy logging and some security and operational metrics, because Cilium can see all the traffic that goes in and out of the pod, as it needs to go through this eBPF program. Similarly to what was explained in this slide here, where each time a process does this syscall, it needs to go through the eBPF program. The same is applied to this to the network traffic that goes in and out of the pod. It needs to go through the eBPF program. And so how does Cilium and Kubernetes work together? This is just a simple overview of the architecture of Cilium. Cilium is running as an agent on each node as a daemon set. And it also has a Cilium operator, which runs as a single instance on the entire cluster. The reason I'm explaining this as an overview of the entire architecture is because we are going to build two images for ARM64. One of them will be the image for the Cilium agent, and the other one will be the Cilium, the image for the operator. The operator is only in charge of doing some garbage collection or some maintenance in the entire cluster for the state that is being done by the Cilium agents. So the agents are responsible for the nodes, for the node where they are running on, and the operator is in charge of the entire cluster where it's deployed. Okay, so let's move to the most fun part of this workshop, which will be to build the images for ARM64. So first of all, the overall steps are in this repository, github.com/AANM/conferences. You have this short URL here where you can follow, you can copy paste the instructions from this repository into your own terminal. So some system requirements for this workshop: we will do the clone of github.com/helium/helium. It's assumed that you already have Docker installed with 1903 with build X, and you have an account in any of these public container image repositories, such Docker.io or Quay.io. And we will build and push the images using this simple command that is going to be executed inside the Cilium repository. So first of all, let's go into this website. So it's git.io/J capital J, capital U, capital Y, Q, and 7. Or if you go to github.com/AANM/conferences, is 2020/10 ARM DevSummit, and then you go to the README file. All right, so first of all, we need to do a clone of github.com. A clone of the Cilium repository. So let's open a terminal for this. We need to create the directory. It doesn't matter where the directory exists. So I'm going to create it into the temp directory. I'm going to go to this directory itself, and I'm going to do a clone github.com/cilium.git. This will take a little bit of time, and then we need to change the directory into Cilium and check out this specific tag. Okay, so we need to change the directory, and now we do git checkout into this specific tag. Okay, now that we have Cilium downloaded, so let's make sure we have Docker 1903. So let's do Docker version. Yes, we do have 1903, and we need with buildx. So we need to go into this website here and download the specific binary for your operating system. In my case, I'm using Linux AMD64, so I'm going to download this one. And it's currently downloading. Okay. It has downloaded now, and we need to make dir, so I'm on this tab here. We need to make dir docker/CLI plugins and move the binary that we have downloaded, which in my case it's in this directory, into the directory that we have previously created. docker CLI plugins, docker build X. Okay, and then we need to change the permissions so that we can use it as an executable. Okay, there we have it. Executable, and we can execute this binary. And lastly, we need to set this environment variable, CLI experimental enabled. Okay. We also need to make sure that we are logged into our Docker account. So let me do a Docker login. Okay, login succeeded, so I'm already logged in. And now we just simply do make images, Cilium image, operator image. So this will build the images for the Cilium agents that are running on all nodes and the operator image that is running in the cluster. And we also want to push as soon as the images are built into the Docker, into our Docker repository. And the images are going to be pushed into these registries here. So Docker IO/AANM. In my case, it will be /AANM. So you should use your own username from Docker Hub here. You type enter. This will take a little bit of time. It might take at least 5 minutes, 5 to 6 minutes, because we need to download the base images from Docker, which are going to be used to compile Cilium. Then we need to compile each Cilium component in the Cilium image and the Cilium operator image, and after that we will push these images into Docker Hub. So if your machine is not going to be fast enough, don't worry. You can use the image that I'm going to build in this workshop. And if you have any questions, feel free to ask during the image build process if you are getting any errors or anything like that. So I'm just going to wait until this finishes on my own machine, so we can later deploy the images into our own, into the VM that was given to you before this workshop. So I'm going already just to do a login into my VM that was given to me. And just to get started, so SSH. So this was the private key that was given to you, and the IP address that was given to me was this one. Okay. All right. So as we can see here, this is a ARM64 VM, and we will use this VM to deploy Cilium. This VM is already contains Kubernetes. Do kubectl get yes. Kubectl get pods maybe. Okay, it has a couple of pods already running. Yes. So these pods are still pending. The core DNS pods are still pending because this cluster is missing a CNI plugin. And since we haven't deployed any CNI plugin yet, then our applications are not going to start. But you might wonder why these pods are already running. These pods are part of the Kubernetes infrastructure, and they don't require a CNI plugin to run. They are running as part of the host network, so they are running. They don't depend on a CNI plugin to run because they are running as part of the host namespace. I think if you are also waiting for the images to be built, I think we can still do this section here, which is to install the Helm repository from Cilium. So we just type helm repo add Cilium https / helm.cilium.io in the VM that was given to you. Okay, so we have this Helm repository. So let's wait before we move into any more steps. Let's wait until the images are built. It should take a couple more seconds. So let's see right now, what is it doing? It's compiling Envoy. It seems it's compiling Envoy, and if I recall correctly, after Envoy it should be the operator, which is the last step. So in the meanwhile, if you have any questions about this process, feel free to ask them. I'll be able to answer them in the meanwhile. Okay, now it's pushing the images into the Docker repository. It's pushing the Cilium image, so the one that is going to run on each agent. As you can see, this one. And now it's going to start building the operator image. The operator image will be faster to build. So let's take a look at my Cilium repository. So I log into Docker Hub, and I go into Cilium -dev, which you will have a similar. You will have the same repository name in your account. You click under tags, and you will see the image that was pushed a few seconds ago, and you see the tag v190rc0. And it is built for both AMD and ARM64. So the image process, the image build that we have done in the previous step was done for both architectures, which means that we can deploy the same image tag on a cluster that has multiple architectures running. And this is for the Cilium dev, and the Cilium operator one is almost done. It's still compiling the source code, and it will be under the operator dev. So it will be named operator-dev, and you will see the tag for this operator image that we are currently building. Couple more seconds. All right, so the program is compiled. Now it's pushing the layers into Docker Hub. Depending on your network connectivity, this might be a little bit slower or faster, but do not wait until the image completes. You can use my image name that since I've already built them. All right, so the images are built. Let's just confirm that the tag exists on the Cilium operator. So I'm just going to refresh the page. Tags, okay, there it is. So we now have v190rc0 for the Cilium agent and another for the Cilium operator. Okay, so as in the steps that I did while the image was built, so I SSH into the machine that was given to me, and I verified that it is an ARM64 machine. I did a kubectl get pods, and we can see there are pods running and waiting for the CNI plugin to be available, so they can start running. So let's sorry to decrease the font size a little bit. I hope it's still good enough. Okay, we can see the core DNS pod is still pending because it's waiting for the CNI plugin to be available, and we have installed, or we have added the Cilium Helm repository using this command here. Helm repo add Cilium https column//helm.cilium.io, and finally we are going to install Cilium using the Helm repository. So this command here is for the image name that I've built because it contains my username. So you just need to replace your my username with your own if you want to use your own images, or you can use my username here because the images are publicly available. Right, so I'm just going to copy paste this command here, press enter, and right, so it seems like that Cilium was deployed on a cluster, so let's verify it. Cilium is running on kube system namespace, but let's see all namespaces or -A. And we can see here that Cilium is running and Cilium operator is also running. And in a couple seconds, yeah, core DNS is now starting because the CNI plugin is available in the cluster. All right, and okay, so moving on to the presentation. So we have just done all of these steps. And so what are the known limitations and future work? There is a flag that was set in the Helm, which is this one. Disable envoy version check equals true. So this version, this tag currently does not support layer 7 policy enforcement on ARM64 clusters because Envoy is not currently built for ARM64 clusters. Sorry, for ARM64 environments. And there is a PR that is currently being pushed upstream into the Envoy proxy done by Mikhail Kostecki. And as soon as these PRs are merged, if they are not done already, we will then build an Envoy binary that is able to run on ARM64. And after that, this limitation will no longer exist. And finally, we will publish these official, these ARM64 images and AMD64 images officially in the Cilium/Cilium Docker Hub repository. They are currently being pushed into Docker.io/Cilium/Cilium-dev and operator-dev because of this limitation. And we are currently doing some development work to have the integration of ARM64 complete before we publish them into the official repositories. All right, thank you so much for the time that you have spent in this first part of the workshop. If you want to know more about Cilium, just go into github.com/cilium/cilium or docs.cilium.io. If you have any questions regarding ARM64 or Cilium running on ARM64, please go into this slack.cilium.io on the ARM64 channel, and myself and other colleagues will be available to answer any of the questions that you currently have. Thank you so much for your time, and enjoy the rest of the workshop.
Thank you, André. Something important I forgot. I forgot to introduce the speaker. Let's see what I can put in the participants in. Oh, I can show people in the. Want to show people in the gallery mode. Okay, never mind. So I'm Zhou, enterprise architect from ARM. I also drive ARM Edge computing team, and I'm also the Equino TSC chair. And André, you wanna turn on your camera? So how? Yeah.
Yes.
Yeah.
Hello.
Yeah.
I'm André, and I just gave this presentation.
Yeah. Just trying to show you. Okay. And
KubeEdge is a project under CNCF.
I was gonna introduce Dave and Lizan and Zhou, who are the experts for KubeEdge, Istio, and Envoy. So you guys, well, we're gonna go through your sessions anyway. So any questions for Cilium so far? Did everybody install successfully on ARM64 in one big? Okay, I see none. Okay, so let's continue with the KubeEdge.
KubeEdge is a project under CNCF. It's based on the Kubernetes and provides infrastructure support for network application deployment and metadata synchronization between the cloud and edge. It's just been promoted from a sandbox project into an incubator project. So before we take a look at the KubeEdge, let's see the major challenges that need to be resolved for the edge computing. The first one is the network reliability and the bandwidth limitation between the cloud and the edge. It's common to see that edge devices are spreading across different regions and different locations. So the network reliability and the bandwidth cannot be guaranteed all the time. The second one is the resource constraint at the edge. The edge device is normally the device like the camera or traffic lights. It's a very small device and don't have enough hardware resources. Edge devices is highly distributed and need heterogeneous device management. So what KubeEdge provides? KubeEdge provides seamless cloud and edge communication for both metadata and data. This is implemented by several controllers. This controller extends the capability of the Kubernetes controller. Next one is the edge autonomy. So KubeEdge makes it possible, makes the autonomous of the edge possible even during the descalation from the cloud. This is achieved by the data persistency of the edge devices locally in a database. No resource ready. KubeEdge can work in a constrained resource situation. No memory, no bandwidth, no compute. For example, KubeEdge can work well on Raspberry Pi. We have done some comparison between the KubeEdge and the Kubernetes on the edge side. So the memory footprint for the KubeEdge is less than half of that of Kubernetes. Simplified device communication, which means easy communication between the application and the device IoT and industrial IoT. So KubeEdge currently supports Bluetooth protocols and other protocols like Modbus. KubeEdge can also support other kinds of the protocols. So this is the KubeEdge architecture. The upper layer is the cloud, and the lower layer is edge. On the cloud side, KubeEdge needs the most of the control plane from the Kubernetes, and also here is a service which is named Cloud Core. So this service is this service includes several components: edge controller, device controller, sync controller, and cloud hub. So the edge controller is extended Kubernetes controller, which manage edge nodes and put metadata so that the data can be targeted to a specific edge nodes. The device controller is extended Kubernetes controller, which manages devices so that device metadata and status data can be synced between the edge and the cloud. Sync controller periodically checks the data that persists on the edge and the cloud, trigger reconcile if necessary. The Cloud Hub is a WebSocket server responsible for watching changes on the cloud side, caching and send messages to Edge Hub. On the edge side, here is a component which named Edge Core. So Cloud Core talk with Edge Core based on the WebSocket or Quick. So KubeEdge has the default configuration for those protocols, and Edge Core connect with your devices based on top of the event bus. So the event bus is on top of the MQTT protocols, Mosquito here. It's offering publish and subscribe capability to other components. So your device can talk with Mosquito directly, or you can talk with mapper. So KubeEdge has a mapper which is named the device mapper. This device mapper has the default implementation for the protocols of Modbus and Bluetooth. And KubeEdge support not only Docker, it also supports other kinds of the lightweight container runtime, containerd, and CIO. And KubeEdge introduced a CSI driver to keep extensibility when integrating CSI plugin on the edge. And here is a layer named Edge Mesh. So the Edge Mesh is to support service mesh capability on the edge and microservice communication across cloud and the edge. User adoption. KubeEdge has been adopted by many organizations. We can name a few: ResCom, WorkCloud, Xinhai IoT, KubeSphere, Huawei Cloud. And here is an example of the highway ETC system. So in this use case, KubeEdge is used in its highway electronic tolling system. This KubeEdge-based ETC system has managed more than 15,000 edge nodes, consists of x86 and ARM devices. The electronic tolling application running in more than 500,000 containers and process more than 300 million data every day. According to the traffic statistics, the average time for a car to pass a toll station is reduced by 86% from 15 seconds to 2 seconds. Similarly, the average time for a track to pass a toll station reduced by 89% from 29 seconds to 3 seconds. The system saves even more time during traffic congestion. So this example has been talked in Cloud Native Watch Summit in China as a keynote speech.
Okay, thank you, Dave. So Dave, you're online. So next, are you gonna show us how to do the hands-on? So shall I stop sharing and let you share?
Yeah.
So can anyone set Dave co-host so he can share? Yes, you started share.
Okay.
Yeah.
Thank you, Tina. This is Dave. Dave Chen from China. I'm the maintainer of the KubeEdge and the reviewer of the Kubernetes scheduler. So today I'm going to give it hands-on about the KubeEdge. And next I will show a demo. Well, the demo is a simple, is a very simple demo which show how to using KubeEdge to connect temperature from the edge and the report and upload the temperature to the cloud. Okay, and I have two ARM server here. This is one running with Ubuntu 16, but it's okay with 18. And it's ARM64. Because KubeEdge is based on the Kubernetes, so first of all, you need to install Kubernetes. I will paste this link to the chat box. Sorry. Okay. Okay, I will paste it later. So install Kubernetes is very easy. So you just need to install some basic components to install one node Kubernetes cluster. So just paste the command here. Okay, next I will install Kubernetes based on the kubeadmin. Oh, it's not clean, so I need to remove this directory. Try again. So it's running already. Need to reset it. Okay, It will take a moment to finish the process. Just copy these commands as it suggests. Okay, so we can see we have one node ready. This is the cloud node. And next, I'm going to install the CNI plugin. I'm using the Calico. So it's okay to use other CNI like Flannel or the Cilium. So this is everything we need to do before we start the installation of the KubeEdge. KubeEdge provide different way for the installation. So let's go to the source. Here is a lookup scripts. You can install the put up this cluster based on these scripts, or you can just install based on a binary, which is named KadMe, which is very similar to the Kubernetes. And another way you can build different binaries on the cloud and the edge and start the service on edge and the cloud. So today I'm just going to show install the KubeEdge based on the KadMe. So first of all, I need to make the KadMe binary. So then I will get the KadMe binary here. So I need this binary to set up the cloud node and the edge node. I have copied the binary here on the edge. Here. So this is the edge node and this is the cloud node. I have wrote a demo, very simple demo scripts here maintained in the GitHub. So I will set the link later. To install the cloud, we just need to run this command and replace the advertising address with the IP address of the cloud node. We will download some binaries, pre-built binaries, and also some YAML files. Those YAML files will be used later to create the device model or the device instance. Okay. And next, I'm going to get the token. The token is provided by the KubeEdge cloud. And this is the token. And on the Edge node, I just need to run this one. This is the IP address of the cloud node. A token, pass the token here. It's downloading some pre-built binaries. Let's say Edge call is running. Edge call is the service that needed for the Edge node. Let's check it whether it's running. Okay, it's running. This is the Edge call service. Okay. On the cloud node, let's check whether the Edge node has been registered. This is the Edge node. It has been registered to the cloud. So we can see two nodes here. This is the cloud node, and this is the Edge node. Okay. This is the overall process to install KubeEdge on ARM64. There's no difference with X 18.6. So just one thing need to mention is that if you are running, if you want to deploy KubeEdge on the Raspberry Pi, which is very which might don't have many hardware resources, you might need the cross building. You might need to build the binaries on the powerful server and copy the binaries to the Edge node. So let's run a very simple app deployment here. It's just Nginx. You can take a look. And it's mapping the host port 88 and 99 to the container port 18. So let's check whether we can create the deployment here. It should be created on the Edge node. Let's check where the port is running. It has been scheduled on the Edge node and is creating. Just need several seconds, maybe. Let's get an IP address of the Edge node. It should be running now. It's running. And check it whether it's running on the Edge node. Yeah, Nginx is running. Okay. This is a very simple demo for the installation of the KubeEdge based on the KEdmin. And next, I will going to show a video, which is pre-recorded. So This video shows how KubeEdge get the temperature from the edge side and collect the information and upload the temperature information into the cloud. So in this demo, the KubeEdge is running in Raspberry Pi, and both the cloud and edge is on 64. So this is edge node. This is how the device model is defined. So we need to create a device model and then create a device instance. So this device is running on the Raspberry Pi. And this is a deployment. And by the way, here is a mapper. I need to build an image for the mapper. The mapper uses to talk with the temperature sensor and get the temperature information and send the information to the edge core, and edge core will report back the information into the cloud. So we can see the report temperature has changed from the 25 to 27. This is because I just did some manually change on the edge side to make sure the temperature is rising. So the temperature is changed from the 25 to 27. Okay. I have upload all those scripts into the GitHub, so anyone who is interested, you can just get the scripts from the GitHub. So these scripts just make the deployment very easier, and it has included several ways. For example, you can using KAdmin to deploy the KubeEdge or use a binary. So it provides two different ways. You can hear the first one is set up by binary, and second one is set up by KAdmin. And I have some wrote the README here. So I will send the link to the chat box later. Okay. Thank you. This is my hands-on. I'm going to stop sharing and find how to what is the chat on and set the link later.
Thank you, Dave. Any questions? Besides, I see there are many questions asked and answered at the chat box. If you have further questions, feel free to ask or at the chat box. And with that, I would like to present the Envoy and Istio. Okay.
Hello everyone, my name is Lizan, Zhou. I'm a founding engineer at Tetrate. We are a service mesh company.
Tina, you are not sharing your screen.
If,
I'm not sharing. Oh,
introduce
sorry. Okay. Yeah. For anything goes wrong, please just speak up from the microphone. Because if I'm sharing, I'm not able to receive your message. Turn on one more time. How about now?
Yeah, perfect.
Hello everyone, my name is Lizan, Zhou. I'm a founding engineer at Tetrate. We are a service mesh company. Today I'm going to give an introduce about Envoy, an open source project in CNCF, and a service mesh Istio on the ARM platform. The ARM support is not complete, but I'm going to give a rough introduction on how to use, including the Envoy and Istio. So, yeah. So first, I'm going to talk about what is Envoy. So Envoy is initially developed in Lyft starting from 2015. So it is a cloud-native service and middle and edge proxy. It handles the network complexity for the applications. So the concept of Envoy is make the network transparent to application. So any like network complexity, such as like connection timeout or like retry, those should be handled by Envoy. There's a benefit of this architecture, which I'm going to describe in the next slides. So at the next, I'm going to describe what is a service mesh. Service mesh is the pattern that the application or service that handles the network connection to a sidecar proxy. In this case, we're talking about Envoy. So Envoy is a sidecar proxy in the service mesh architecture. The application connects to the sidecar proxy via some local host connection or Unix domain socket, or in Istio we use IP tables to redirect all the traffic to a sidecar proxy. And then sidecar proxy handles all the connection and talks to the other service sidecar proxy, and they gather a lot of information about the traffic, then talk to the service behind the sidecar proxy via the local host connection. So this is the service mesh pattern that I'm going to describe today, and we have a hands-on later. So let me describe the background of why we Lyft initially developed Envoy in the first, and then why it becomes so popular. In the industry, the microservice networking is really a mess at the moment. And it is hard to debug, and it have some of the a lot of issues. So one issue is there's a lot of many language and frameworks, such as like Python, Ruby, and Go, and we use a lot of protocols. It was the era that we migrate everything from HTTP1 to HTTP2. There's new RPC protocols like gRPC. There's database connections. There's several different RPC frameworks such as Swift, and there's double support in Envoy as well. Infrastructure changed from on-premise to cloud. There's different services, and those comes with different load balancers. Observability outputs consistency is another issue. Different framework, different language generate different observability output. So if you want to have a consistent overview of your microservice, it will become an issue. And also, the retry behavior and circuit breaking or like timeout rate limiting, those behavior are not consistent across the language and they have different best practice. Also, authentication and authorization are handled by a framework. They have small behavior difference. So that's the background when Envoy was initially developed. So this is like heart of rapid approaching at that point. Debugging is also another issue because different languages have different debugging practice, and also it's hard to track the network calls between different services. There's limited visibility into the infra components such as like load balancers, especially like hosted load balancers such as ALB or ELB, the hosted databases, hosted caches. And there's multiple implementation about circuit breaking, retry, and rate limiting. So that was not easy as well. And also at the end, libraries are really hard to upgrade. If you have any CV in each library, you have to rebuild the whole application and redeploy all your application. Just not like Envoy. If you use Envoy as in the sidecar proxy pattern, then you only have to upgrade the proxy and your application can run in the same manner. So Envoy was designed to handle this situation. It has out-of-process architecture, which gives you the easy to upgrade, and also it also has using C++ have a very high performance. It have an easy extensibility feature because it has a clean internal architecture. At that moment, because HTTP2 is also already standardized, it developed in HTTP2 first. It has the service discovery and active passive health checking, have the load balancing, and it also has the best-in-class observability features. It can also handle authentication and authorization with the extensibility that have the external authorization stuff and have some edge proxy features. So one of the key features is the XDS API, which is heavily used in the service mesh context. So what XDS is, the XDS stands for the blah discovery service. So that includes listener discovery service, which means what Envoy listens to. And the cluster discovery service is what the upstream or like what the backend of Envoy is talking to. So it is a universal data plane. And there's also a lot of different discovery service such as endpoint discovery service, route discovery service. So those discovery services are defined in a gRPC streaming, in a gRPC format. So it's a protocol buffers and it has the JSON and YAML mapping. So basically, what you want to deploy is you deploy Envoy with a static same configuration, just point that to your control server. This is a unique feature that you can deploy your application in the same manner, but it points to some control plane, and the control plane gives each Envoy different config, so the Envoy can handle the what's intended the application should talk to, or the traffic pattern that application have. That means you have the same bootstrap config for everyone, for every Envoy, and the rest can be taken care by the control plane server. So this gives the fleet-wide traffic management distributed system. So let's talk about the ARM support in Envoy. It is already ready in the main branch as of July this year. The Docker image for ARM64 is released for every commit in Envoy proxy /Envoy. It will be in the stable release in the next one is 16, which should be released around when you hear this. We release every quarter, around end of quarter or beginning of quarter. It is not released today when I'm recording this talk, but it might be already released when you see this talk.
Hi, Tina.
Oh, I'm
Can
sorry, I was
choose?
muted. Okay. I was saying, yeah. So you want to go for the hands-on of Envoy first, or shall I play Istio?
I can do some demo about Envoy. I will share my screen.
Are you sharing?
Yeah.
Change out the co-host, all right? Okay, here you go. Thank
Can
you.
you see my screen?
Yes, I can.
Yeah.
Okay. And actually, I have two hands-on about Envoy. The first is how to build Envoy on ARM64 platform. And the second is a simple Envoy proxy demo. And okay, let's look at the first Envoy, how to build it. And well, okay. This is my ARM64 platform. Okay, I will show some information about my host. Okay, and you can see this is a SandX2 platform. The architecture is ARM64, and this is Envoy repository. I just clone it just now, just a few minutes, and I built it and in last minute. And, I will use this command to build. And actually, the build Envoy binary have two ways. There are two ways to build the Envoy binary. The first is build the binary on bare metal host. The second is build the binary with Docker help. For the binary for the bare metal host, you need to configure some compiler tool chains and install Bazel tools. If you are expert or want to be a Envoy developer, it's a good choice. But if you are beginner, if you are freshman for the Envoy, I'm strongly suggest you choose a later one. Build and test the Envoy by the Docker. And it's because the configuration is very easy. Okay, and this is a command, clone the Envoy repo from official repo, and cd, and this is a shell to build the Envoy binary. Okay, that's it. Actually, the command is same with x86 platform. You can see this is a building process. Maybe there is a little issue about it. Please check it. And there is a little issue, but before the presentation, I have built the Envoy successfully, and please check it. And you can see we built this with a Docker image. In this script, it will invoke the build binary, just Envoy build map binary. It will invoke the Envoy build Ubuntu image to build all the Envoy binary. In the end, the binary will be at the folder. Please check it. Will be at build release script. This one. Oh no, not this one. Will be temple envoy source. Oh, at here. The Docker will build the Envoy at this part. Now we can run this Envoy on ARM64 platform for a test. You can see this is just a build on October 8. Okay, this is the first demo about how to build Envoy. And the second demo, the second hands-on is Envoy run Envoy as a proxy. Okay, just like this command, and we will run it on the ARM64 platform. And it will, it is a proxy on the internet. It will, if you access this host, it will transfer your access to the Google website. We will run it on our ARM64 platform. Okay. This is our test platform, the Ampere server. We will run this platform information. Sorry. You can see this is Ampere server. The architecture is ARM64, and there is a another requirement about Docker. We can see there is also Docker version 19.003. Okay, we will run this command just like a slice. This one. This is an image, and we have been downloaded in the local site, in localhost. We can. Envoy DEV is a local image. Okay, we'll write. It will transfer your access, your request to the Google website, and you can we can get the host name is night ampere 01. Okay, and then we will get it. Wait for a moment. We will get it from a website, and we can see that. Okay, you can see we visit the website night ampere 01 Shanghai .com 10,000. Okay, we do some research. Hello world. Okay, but the Wikipedia maybe not. Yeah, it's a redirection. Okay, we can also find some images. Okay, so this is a proxy, Envoy proxy. So that's all demo about it. Yeah.
Any questions, comments? Yeah, it's a very hot service mesh, and it's used by many occasions. Okay, if not, I would like to share the
Excuse me,
Istio.
I have a question. Can you hear me?
Yes.
Okay. I have a question to Li Zhao about Envoy authorization control. So here actually, I appreciate Li Zhao's presentation and the demo about how to build and deploy Envoy locally. But my question is more about how to integrate with Envoy with Istio, of course, and Kubernetes. So I don't know if any high-level orchestration is already available for the user to set up or integrate with third-party authentication and authorization center or some other plugin or modules. For example, can you hear me?
Yeah, I can hear you. Please go on.
Okay, so my question is more about how to, if any channel or service or API already exposed for Envoy's authentication or authorization support to integrate with third party.
Actually, I'm as far as I know, the Istio is a component, include a component for the authorization. Envoy only responsible for the transfer, but I'm not very familiar with Envoy this part.
Okay.
It sounds like we need a second workshop to solve that problem.
Yeah, that will be right.
yeah, encourage you to keep discussing in the chat box or like get offline. With that, let me play the Istio intro. Here we go. With the full screen.
Okay, next I'm going to introduce Istio. Istio is an open source project that developed by Google, Lyft, and IBM. The ARM support of Istio is still in progress, which is not ready today. So I will give you some overview of how Istio works, what it provides value. Because it is not ready today, this is not included in the hands-on today, but we should be able to expect that to be available soon, since the hardest part, which is Envoy, already has ARM64 support today, and that will be included in the hands-on. The control plan of part of Istio is written in Go, so I don't expect it will be too hard to add ARM support, but just not available today. So what is Istio? The problem, which is I already described in the previous slides in Envoy. So Envoy provides a data plan of that part, but in the last slide of the Envoy configuration management, I said that Envoy is able to talk to the control plane server to get the configuration. But so who do the configuration disk delivery, or who manage that? That is Istio. So Istio uses Envoy as a data plane. It provides the configuration that Envoy needs, so it can provide this monitor, secure, connect, and manage the service in a consistent way. So let's talk about the monitor first. This is usually the first feature that the when a company or admin introduces Istio, and it's easiest, the first part that people can use. It's basically help you to understand what's actually happening in your deployment. That includes the metrics, logs, and tracing. Because the data plane is Envoy, it gives you a consistent output regardless what language or framework you use for your application. So it gathers the information from the network. And also the security part. So Envoy is an out-of-process model, so it still provides the key provisioning, and it gives the workload identity as in layer 7, or say in TS. It does TOS key search provisioning as well as HTTP authentication, such as JWT authentication, that provides a service-to-service authentication and authorization. And connect. This is the networking part. So it includes a service discovery in Kubernetes. This is the service discovery information is getting from Kubernetes API server. It provides a configuration for retry, outlier detection, circuit breaking, allow you to configure client-side load balancing. So those are the network feature. So manage, basically it control which requests are allowed and where they flow. So this is also, again, this happens in layer 7, which is not L4. This is very important part in context of HTTP2 or gRPC, because in HTTP1, there's only one request in one connection at one time, but the HTTP2 or gRPC is a multiplex protocol. So that means if you don't understand the application layer, you cannot do the fine-grained control of gRPC or HP2. You can also provide a lot of policy on those requests, like authentication authorization that I said before, or rate limiting, and also like load balancing policy based on the request metadata, which can define in Envoy config, and that is converted from Istio config. So how this works? So in this slide, the top half part is essentially the same as the service mesh. What the slide that I've presented in the previous slide. What is service mesh, right? And then the control plane API here is Istio D, which contains the like config data, and pilot is Pilot and Citadel, which is like in older versions, those are separate components. Since in newer Istio version, this is merged into same component called Istio D, which gives Envoy like different configs. The Citadel part is giving Envoy TLS certs and private keys, and then Pilot gives the service discovery informations. So this allows the Istio give Envoy configs for the features that I described before. So there's some non-limitations, as I said in the first slide. The data plane is Envoy, while Envoy has the ARM64 support today. The Istio proxy, which is basically Envoy plus some Istio Envoy extension, haven't got official ARM support yet. We're also making a big effort of supporting WebAssembly extension in Envoy, which is leading by Istio community. So that one doesn't have official ARM support yet. Control plane is written in Go, so I expect it will be easy to build. It's a pure Go program, but we don't have any testing or any official Docker image for them either. Of course, you can also use like run control plane in an Intel platform and just run data plane on ARM or vice versa, or having some mixed Kubernetes environment or mixed VM environment. They should be able to work. But again, we don't have the those available in the official registry, and testing haven't been done. If you're interested, you can contribute to the project. Okay. So.
Thank you, Lizan. And so I think this is partially answered the questions from Xinhui from Salesforce just now about relationship and combination of Istio and Envoy. And any questions, comments?
Yes, actually, the part is better related to WebAssembly piece is related to my question about authorization piece, actually, more accurately speaking. So where I'm wondering if, have any reference links I can find the referred 3 data plane, modules Lizan just presented?
We can send you offline. Yeah, go ahead.
I can send you the website to you about the Istio component, which is responsible for the security. Yeah.
Okay, that will be very nice. Thank you very much.
Yeah, thank you. Yeah, That would be awesome. All right. So Ines, are we on time?
Yeah, we did a little bit more than an hour 30, but I think it's fine. If nobody has any more questions, I think we can end it.
Okay, cool. Thank you for all the speakers, André, Jingjiao, Dave, and Lizan, and thank you for all the participants, and especially those participants and speakers from China. It's midnight, I know, and it's a international holiday, Golden Week holidays. Thank you, everyone. Appreciate. Hope to see you in all the ARM64 Slacks of the Cloud Native. Thank you, Sydney. Thank you, everyone.
Thank you.
Bye. See you
Thank
next year.
you.
Bye.